Okay, hello class, welcome back. Today I have a new problem for you. I would like you to find the dimensions of a rectangle inscribed inside of a semicircle with radius 5 that will result in the largest possible area. So what I'm asking right here, largest possible area, that is our first step, our dead giveaway. We are trying to optimize, find the max area. Do we agree? I'm trying to find the maximum area of a rectangle. I guess I should also write a little rectangle. Yeah? So, let's dive into this. We need two equations. What is the equation for the area of a rectangle? Well, area of a rectangle is oftentimes length times width. That's a basic kind of sixth grade math. We learned this a long time ago. We're used to it. We like it. So I'm going to kind of look here at my diagram. Well, in my diagram, I have x distances. We agree. And then I have like y distances. Hence the coordinate point x comma y. Well, my area is going to be this entire baseline down here. That's the length times this entire height line, or the width, so to speak. So I'm going to kind of change this up. Instead of saying area is length times width, I'm going to make the statement that area is equal to 2x times y. So just kind of summarize the variables that I'm using. Okay? This is my optimization equation. Now, of course, I have been given some information. Let me tell you my given statements. I have been given the constraint that we are stuck inside of a semicircle with a radius of 5. Now, I'm going to help you guys out. The equation for a semicircle is similar to the equation of a circle, but we just solved for the variable y. So my radius 5, well, in the equation of a circle, it's like x squared plus y squared equals the radius squared. So I'm going to be left with the square root of 25 minus x squared. Okay? This is the equation for my semicircle. That equation will define every single little point that goes around this circle. Everything can be defined by the equation y is equal to the square root of 25 minus x squared. Okay? Well, this is actually really convenient because we notice, what do we have? Well, I have a y and I have a y. And when we optimize these equations, we want to make sure we just have one variable for now. Okay? So I'm going to go ahead and make this substitution like follows. I'm going to say that area is equal to 2x times, and then for y, I'm going to substitute in this equation, 25 minus x squared. Okay? This is my optimization equation. Now remember, I want to find a maximum, the maximum of my area equation. And the way we find a maximum is by looking at the critical points. I know you guys remember how to find critical points. It means that we want to take the derivative. You can think about this a prime, that notation. Maybe maybe your teacher might use the notation dA dx, also works, okay? We want to take the derivative. Now, if we notice this equation, this is one part times another part. So you guessed it, we have to use the product rule. The product rule says the derivative of the first term, which in this case would be 2, times the second term, square root of 25 minus x squared, plus the first term, 2x, times the derivative of the second term. Now, the derivative of the second term. Now, I know if I have a square root sign, it's really a 1/2 exponent. Hopefully you guys will recognize all of this, but what I'm doing is I'm taking the chain rule, the derivative around my function, and I'm going to multiply it by the derivative of my function. The derivative of 25 minus x squared is just a negative 2x. And I'm left with this statement. Now, I know this is not the most pretty. the prettiest of equations, but you know, I think if we manipulate it enough, we can make it look pretty decent. So let me bring it back. We want to find critical points, which means we want to set this all equal to 0. I'm going to simplify a few things. I'm going to write this as 2 times the square root of 25 minus x squared. And I'm going to write it over 1 just for now. Plus, and a couple of cool things are going to happen. The first thing I notice is I'm going to have, well, I notice this 2 and this 2 are on different levels. So I'm going to go ahead and cancel them out. And I see that this x and this negative 2x are going to end up multiplying and being in the numerator. Now, I say in the numerator because the fact that this is a negative x squared means this now all goes into the denominator. And I'm going to write it back with this radical sign notation, just like this. I can say it's equal to 0. Now, personally, I see this as a fraction plus a fraction. I like fractions, but I think fractions like each other. So I want to multiply this fraction by the square root of 25 minus x squared. So I get a common denominator. I want to bring these fractions together by addition, and I can't do that unless I have a common denominator. Now, a cool thing is about to happen. Notice that this term, the 25 minus x squared, is going to be multiplying another square root of 25 minus x squared. Well, if I multiply two roots, what happens is the roots will cancel with each other, leaving me just with this inside piece. Do we agree? So now I have, again, this 2 follows me, and I'm just going to be left with this 25 minus x squared minus 2x squared all over the square root of 25 minus x squared is equal to 0. Now I'm looking for critical points. I want to see where does this derivative function equal 0. So let's look at my numerator. Let's bring my numerator around. I am going to clean this up a little bit. I can simplify. This is really 50 minus 2x squared minus 2x squared is equal to 0, which is really 50 minus 4x squared is equal to 0. We can take this 50 away, and I'm ultimately going to divide out this negative 4, and I should get x squared is equal to 50 over 4. And as we all know, to find x, I can just square root everybody. So x is the square root of 50 over 4. I know that may be driving some of you guys crazy. Feel free to reduce it. I know you guys can. Yeah, and so I get the 5 root 2 over 2. And this is my x value. Now, I'm pretty sure that's a minimum. Let's go through and check a couple of things. If I have 5 root 2 over 2, I can pick a number a little bit larger than that. Now, 5 root 2 over 2 is an interesting looking number. I imagine this is going to be something a little bit larger and a little bit closer than 7 over 2. Really close to like 7 over 2, which is like 3.5. So this is like really close to 3.5, a little bit more than 3.5. If you want to type it into your calculator, you can. I just did, actually. It's 3.54 if you're curious. So I'm picking a number larger. Let's go with 4. A number a little smaller. Let's go with 3. And I want to plug these values into which function? My derivative, my dA dx function. Okay? So that means that's this function right here. This is the function I want to plug them into. So when I plug a 3 in for this x, and this x, I actually get a positive value. I'll let you guys try that out. Okay, plug a 3 in there into your calculators and try it out. See what you get. You should get a positive value. And when you plug a 4 in there, you should get a negative value, meaning decreasing in my function. So since we were increasing to decreasing, we can confirm by the first derivative test that when x is equal to 5 root 2 over 2, we have max area. But we're not quite done. Let's take a journey back. I'm going to scroll for a while. It's a long problem. Let's take a journey back to the problem. It says find the dimensions. So I'm looking for this purple area that I've circled. I want to know how tall is this, and I want to know how long is this. And all I've solved for is this. I solved for x. We, back in the day, said x is 5 root 2 over 2. Well, that means the entire length, my length, is going to be 2 times 5 root 2 over 2, which is just equal to 5 root 2. And how do you guys think we can find this y value, this height value, my width or my height, my y, whatever you want to call it? Well, earlier we had a given statement. I had this wonderful given statement. Don't forget, it was a given statement. And it said y is equal to the square root of 25 minus x squared. So if I want to find my y value, I can take the square root of 25 minus, and now I can put down 5 root 2 over 2 squared. I typed this into my calculator, and you will be pleasantly surprised to see that you do get 5 root 2 over 2. You get the same value, okay? You get 5 root 2 over 2, which is kind of cool. So did we find my dimensions for length and width? Absolutely we did, and we did so using calculus. We used that first derivative test. We put it to the test. I hope you guys enjoyed this. This is a great practice problem. It used an equation as my given statement. Everything else was very basic in the sense that we know what area is. That derivative, that was a good, challenging derivative. The differentiation was not necessarily the hardest, but it was not easy by any stretch of the imagination. And we had a lot of algebra skills involved. All right, guys, I hope you guys are practicing. I hope you guys are working really hard. If you guys need anything, feel free. Drop me a comment, send me an email. Have a great day.